Hi, everyone. My name is Luyu Cheng. Today, I'm going to introduce a new perspective into debugging and testing compilers. Compilers are a kind of sophisticated software. It takes a bunch of source code files and produce one or more programs, sometimes libraries. The implementation of compilers are intricate as they consist of many stages. This makes compiler difficult to be tested as a whole. A common practice of test is to compose a large quantity of source files and then execute the compiler on them. We can either test the properties of compiled programs, or we can collect the output from the different stages and compare them with some expected results we already written. This is not an easy and trivial task. Therefore, there exists many test suites which can help compiler developers test their software. Each of them has thousands of source files and expected outputs. However, emerging languages can only make their test suites by hand. For example, Rust's compiler has a set of UI tests. Each test contains a source file which indicates the line where errors or warnings are expected. Together with them are expected output. For example, a file describing what is expected from the standard error output. So the Rust compiler should produce the exact error message matches the output. We believe that this traditional method of compiler testing and debugging is not very developer friendly. So first, a test file can only be considered as a test case, which is either expected to succeed or fail. However, we may want to conduct multiple tests in the same program and with the same context. Then, each test file is usually not written in one go. Developers need to go through a cycle of writing, running, and inspecting. Moreover, they usually have to switch between the text editors and terminals to view the results. Lastly, the compiler tests only record and compare the output from the standard output. As the compiler has many stages, and we cannot check and compare the intermediate results of a specific stage, this makes the test completely black box. Therefore, we propose Diff-based testing. Although it is still based on plain text, we argue that it can address the aforementioned shortcomings. Okay, so since time is limited, let's start the lab demo. Let me change the... Okay, I want to turn on the mirror, but it doesn't work. Yeah, I want mirror.
I think from here, there's a top level.
Yeah.
One of these is mirror?
No, that's weird. Okay, let me see this. Ah, I see. Okay. Yeah, okay, cool. So here we are working with a test file of the ML script compiler in VS Code, and each test file is organized into multiple test blocks, separated by one or more blank lines. The test framework will continuously monitor the test file changes in the test directory. So whenever you save or modify a test file, the test framework evaluates each test block in sequence. This allows the latter blocks to reference the variables and functions defined in previous blocks. For example, in the third block, we can refer to the two functions defined in the previous blocks. So let's go ahead and save the file. Let me turn on the, okay. Oops. Oops. I guess I might run the wrong program. Ah, I see. Sorry. Yeah, okay. So now, as you can see, the test framework automatically writes the results as special comments directly into the test file. By default, it logs the inferred type and the evaluation results. Now, if we add a new test block right after here, for example, you can see that the results will be instantly written back into the file. But what happens if we make an error? For example, we can change this to a string, but the function accepts an integer. If we save, you will see that the test framework detects this type error immediately and right after the test block. So this makes the experience feel very interactive, providing real-time feedback. So it's almost like we are using an interactive notebook. Sometimes, though, errors are intentional in compiler development, so we can actually use the debug flag here, the debug flag here, to mark the block as the error in this block as intentional. Additionally, there are other test flags, for example, PE for parsing errors and RE for runtime errors. These debug flags are also used for exploring intermediate stages of the compiler. For example, we can correct the error here, and we can use the JS command to see the compiled JS. And also with the DP flag, which means debug the parser, yeah, we can say that we can access the detailed logs from the parsing stage. This tree-like log review the function called hierarchy and the state changes during parsing. Yeah. The debug logs serve two key purposes, debugging and change tracking. Many of these logs are committed to version control, making it easy for developer to see how their changes impact the compiler's behavior. The test framework is also integrated into our continuous integration pipeline, ensuring that we don't forget to update the test files. However, these logs can sometimes get quite long. For example, here we are looking at a log. Let's use the DP flag to review the debug flag. It is very lengthy. We can activate a side panel with interactive tree view of the logs. From there, we can search and filter specific function that we are interested in. And clicking on the logs, the button here, can even take us directly to the relevant source files where this log is happened. This interactive view stays in sync with the test files. So in practice, this setup is often more efficient than traditional debugging tools, as it eliminates the need to constantly switch between debuggers, code editors, and terminals. So with this live feedback, we can stay entirely within the code editor. Okay, so I think my time is up. So this is the end of my talk. Thank you.